Hello, everyone. My name is Jinho, as introduced. My co-authors are KK Ramakrishnan from Rutgers University and Timothy Wood from George Washington University is my advisor. And my paper is NetVM. We achieve like high performance and flexible networking using virtualization on the commodity platforms. Let's move on. So everybody loves the high performance networking. So what are the like line rate high performance machines out there? So we always buy like a special hardware and the software comes together, very expensive cost. You have to pay like a lot of money, and it's really hard to upgrade, replace, and scale it out. So people try to get the better machines in the commodity servers. So I show you some of the examples like a package shader and Silicon 2010, and the authors are here right now. So I'm gonna say the good things about it. So they leverage like a GPU and chips like a 40 gigabps. It's really good. And next system is an NMAP ATC 2012, and they run on the commodity servers and achieves a very high performance. Also, Intel released DPDK, the data plane and development kit. They run on the commodity servers and the commodity NICs. So we have a question about with all these systems. So data centers are deployed into the virtualized platforms. We can ask like the performance in the virtualized platform. What is about it? And we can think about this overlay model that if the package comes into the system that goes from the NIC card or the host operating system, virtual switch, virtual NIC, and the guest operating system, and the guest user space. And the application processes it, it has to go all the way down to the NIC card again through the same path, right? So it has we have a lot of overhead that then we have to overcome to deploy these systems in the virtualized platform. Okay, with this, the people come up with ideas like how to, deploy these functions. There is the fancy name called like a network functions virtualization. So people try to come up with the idea how to do it. To compare, we have existing network functions like a router, the firewall, load balancer, and CDN, a content delivery network, and the data deep packet inspection, and the WAN accelerator. So if you think about these functions come with a special hardware, we have to pay a lot of costs, like 6 machines, times power, and the times hardware cost and the software cost. So we have to pay a lot, but instead, if we have like a virtual platform, you deploy these functions on the top of the virtualized platform that you can dynamically deploy it, and you pay like a cost, very less cost, like 1 machine and the power, the software only. So if we have these kind of very good systems, but still we have limitations in performance, right? So we have to provide very good performance to have these network functions in order to process packet in the fast way. So we have to overcome that. And if we look at these each functions independently, they run independently. But if we, figure out how they are related in terms of like a processing packet, so they always like a sequentially processing packet in the network. So the packet comes into the network, they process like a deep packet inspection, firewall, and an accelerator, router. All these like a sequential processes are like, handled by each servers. But if we deploy this in the virtualized platform, we probably have opportunity to the process in a way that in a parallel way, or we process the packets between these the functions in a fast way, right? Gives us more opportunity to do that. Also, we can deploy network functions in a dynamic way. So if we need more functions, you can just deploy it and hook up with the other functions in the processed packets. So it gives us a lot of opportunities. But still, the problem is that we cannot achieve as good performance as existing systems. So in this case, we have to overcome like a high-speed inter-VM communications to deliver the packets, among the different functions, right? So with all these 3 challenges, so what NetVM has done, NetVM is a platform for running complex network functionality at the line speed. We target like a 10 gigabps at the beginning, and using commodity hardwares. So the NetVM actually retrofitted KVM and DPDK with a series of innovations like as follows, like a virtualization-based high-speed packet delivery, and memory sharing framework for the network data, and hypervisor-based switching, and the high-speed inter-VM communication, and the security domains. Before I go one by one, I'm going to introduce some of the backgrounds that what platform we are actually implementing this. Okay, so we target the COTS, commercial off-the-shelf servers, so you can buy like online, And we also utilize the DPDK. It is a set of to optimize the user space, the software and the library, then it allows us to access NIC card directly and avoid this overhead incurred from the Linux kernel. So to compare, the user applications actually receive the package through all these functions. So once the packet comes into the system, the operating system needs to handle it, and it has to handle the interrupt, and it delivers the packet by copying the packet to the application. Application also has to system call to the operating system and copy the packet into the kernel space, and the kernel space can send out the packets. However, the DPDK actually provide all the complex functions in the user space, like buffer management, ring management, and the poll mode driver, and packet classification in the user space. So the application actually runs on the top of these libraries, the drivers, so they can actually pull the NIC card and get the packet directly DMA to the application space, and they can handle it. So we avoid this overhead incurred in the three steps, like a packet copy, interrupt handling, and the system calls. So it gives us the good way of processing packets. Okay, so DPDK with the virtualization. What kind of architecture we can deploy with the DPDK, the virtualized platform? So we have two variations. The first one, so we deploy DPDK in the hypervisor layer in the user space, and then you get the packets from the NIC card, and then you switch through the virtual switch to virtual NIC, and then the packet is received from the virtual machine and process it. But still, this while this gives us like a flexible configuration and dynamic configurations, and still gives us control over packet switching and the load balancing, still, but it has like a lot of overhead, because once you get the packet in the hypervisor, you still have to go through all the layers that between the hypervisor and the virtual machine. And the second architecture we can think of is DPDK inside the virtual machine, that it gives us a pass-through mode that the application actually directly access to the NIC card, and then it gets packet, actually DMA the packet directly into the user space in the virtual machine. So this gives us like some performance benefits. However, it allows us to have like steady configurations, and inter-VM switch. Inter-VM switch is very limited, because once packet comes into the system, it is always routed based on the L2, the address. So the packet should go to destined the virtual machine with the L2 space, the L2 address. But we don't have any functions, so we can direct the packets based on the contents or header or something like that. Also, once the VMs are sharing this L2 switch, but if they share like different switches, the packet comes into one switch and then go to one virtual machine. Then if this virtual machine wants to forward this packet to another virtual machine which uses another port, then the packet has to go out of the machine and come back to the machine, then forward to another virtual machine. So it's an inter-VM, the packet delivery is not so efficient. So like I said, there's no control over packet switching and load balancing as well. On the top of that, the worst thing is that neither of these systems actually can support like a full line rate network performance in the virtual machine layer. So we try to overcome this by having a NetVM. Let me show you how the NetVM architecture looks like. So this is a simplified NetVM architecture. We actually have a memory shared between the virtual machine, and memory shared between the virtual machine and hypervisor. Once the packet DMA into the systems, we share that packet across the hypervisor and the virtual machines all across, so that we can have a high performance. So let's see the flow of the packet, how it comes into the system. Once the packet comes into the NIC, and it goes to the NetVM first, and the NetVM delivers that packet into shared memory, then it notifies the VM through the ring buffer that there is a packet. It gives information about the location of the packet and the length of the packet and things like that. And then the applications inside the virtual machine that post this the ring buffer, and then it knows where the packet is, and it access to the shared memory to process the packet. So packet can be processed like in a way, then you can manipulate and replace all these things if possible. So we had 4 design challenges to achieve this. The first one was the zero copy. So in the system, once the packet comes in, you don't want to copy it, because it that gives us a lot of cost. You have to pay a lot of cost. So we try to avoid the copy at all. And so huge page sharing. So all the applications, NetVM and the user space application all run in the user space, right? So user space is handled by like virtual addresses. So we have to map in the user space in the hypervisor and the user space in the virtual machine. So we have to deal with this. And also the package should go from one virtual machine to another virtual machine by just sending this descriptor of the package. So we have to share all this memory across the virtual machine. And we avoided all the locks. Our system doesn't have any lock. And we also avoided the NUMA inefficiencies by having the aligned core and queue design. Okay? And the important thing is the security, right? And the virtual machines don't want to interrupt each other, or they don't want to share any data between the virtual machines. So we guarantee like a minimum security between them, so administrators can decide what to do, when they have a different set of virtual machines belong to some other parties. Okay. So let's see why the memory copy, the avoiding memory copy is so important. So if we think about the 10 gigabps, that the 64 bytes, the size of packet, that is interpreted like as the 14 million packets per second. So it should be handled in the systems as like a 67 nanoseconds. But if you see this sample graph from the website here, then as you can see, it shows the time, how much time it takes to copy 100 calls. So if you see the y-axis, that it shows 64 packet size, and it takes like 300 to 400 microseconds, right? So it's a lot higher than the time limit we have to process the packet to achieve 10 gigabps in the system. So we definitely have to avoid the memory copy. So in the systems, we DMA the packet into the huge page shared across the virtual machines and the hypervisors. Once the packet comes in, we never move that packet. We can manipulate it, but we never move the packet. Instead, we deliver the packet descriptors to the virtual machine and across the virtual machine. So only some of the information about this real packet goes across the system and is handled by the application in the virtual machine. Okay? So once the packet is handled in the application side, the application can decide what to do after they process the packet. So the actions are like a chain to another virtual machine that you want to process in the further in the different functions, or you can send that packet out by changing the header, or you can discard the packets in the systems. Okay, so all these actions are provided to the applications to decide what to do after packet is processed. Also, the chained packet delivery is done in the systems. Packets are processed in a sequential way, as I showed in the previous slides. Then applications in the virtual machine pass the packet descriptors across the virtual machine, and this information goes through the packets, and then finally it can be decided to going outside or discard to do, depending on the application. And this packet processing happened only one application at a time, in order to avoid like a multiple access to the packet, but it's possible also, to process the packet in a parallel way if the packet is only handled for the read only, right? Okay. Also, we avoided the locks and the NUMA inefficiencies. How we avoided locks that shows this graph. Then we actually match the core and the queue, and so each core actually uses different queues. So the one core actually handles only one queue, as you can see from the figure. So the different cores like push the packets into different queues. And this is horizontal queues, but if you think about the queues in the virtual machine, which handles the packet directly, and the core in the hypervisor who pushes the packet information to the queue. So they're actually separating the data structure, so they're only reading and writing in their own area. So there is no lock for that. So that's how we solve the lock problem in the system. And for the NUMA architecture, the reading your packet in the one socket to the other socket, it always invalidate the caches. So if you ping pong the packet, you always have to fill up the cache again, and your processing time will be tremendously increased, right? So we, as you can see from the green boxes and the red boxes, they don't share any the structures inside the system. So the one packet actually processed in the one socket all the time. So it goes to it follows the path that is aligned with the one socket process and the queues and everything. Okay. All right. So also, as I mentioned, the virtual address space should be mapped from the hypervisor to the virtual machine. So how we expose this shared memory to the virtual machine is through the PCI device. So the PCI device actually maps this in the linearly. So the consecutive huge pages should be mapped to the non-consecutive the memory in the host. So how we did is that instead of the looping through these huge pages, we just pre-calculated all the offsets the before, and then we just, when packet comes in, we just calculate the instantly with just one line of code. So that's how we avoid the looping. Then we had the high performance in the memory mapping. All right. So we also provide the security domains between the groups of the virtual machine. Some virtual machines can be trusted, some are not. So you divide the shared memory between the groups of the virtual machines. So you only allow the virtual machine belonging to a trusted domain can see the packet. So other virtual machines not belonging to your security domain don't see that shared memory. So there is no harm to the shared memory between the trusted virtual machines. That's our assumption. Okay. Also, non-trusted VMs just handle the packets in a general way. All right. This is the NetVM the implementation. We had the overly like 4 components. The first one is NetVM, the manager. It handles like about the creation of the virtual machine and destruction of the virtual machine. So it monitors that, and it also knows what kind of functions inside it. It gives information about their functions to the virtual machine, so the virtual machine and the application in the virtual machine can decide which function will be used for the next process. These things. Okay. Also, the NetVM core has all about the DPDK. It has a handling of the shared memory. It has shared queue handling, and so it interfaces to the PCI and it delivers all the packets and does the core things. And the emulator, the PCI device actually exposes the memory in the hypervisor, and it also has proprietary the ring between the virtual machine and the hypervisor, so it delivers like a packet descriptor between. Also, the last one is user NetVM library. We give a user the application and a convenient library, so user don't need to worry about the underlying structure, about the queue alignment or the core queue alignment or these things. So user only accept this packet and they process it and simply handle that packet and send it out by having decisions. Okay, let's move to the evaluation. We used the 2-socket Helm architecture machines, the 82599 Intel NIC, and the 2 processors and the 6 cores inside. We didn't use hyper-threading. And the 2 cores are assigned to the receiving packets, and the 4 cores assigned to the transmitting and the forwarding. And total, we used the 8 gigabytes. The huge page is 4 for each. And only 1 port is used, and the application was L2, L3 folder, and the click user space router, and the firewall, and the packet generator is used. The packet generator comes from the window river systems. So this graph shows how the NetVM performed. As you can see, the NetVM increases the forwarding rate as the input rate increases, so it's linear. We expect like more port to add it to the system, it will increase that's linearly. However, the click NetVM shows like a 6 gigabps achieved, and then it has overhead and dropping the packets and then slow down from there. So the click NetVM is like a modified click that we add the elements in there to interface with our systems. The SRRV is like original system from the DPDK that it achieves like almost 5 gigabps. Then it slowed down after that. Is dropping the packets, and native click, the click native Linux runs in the physical boxes, and then it shows the poor performance because we actually did not optimize this the click, because you want to see how the click performs after my session. There is a click OS presentation following. You will see the real performance, and this shows like how the system performs when the packet size is changing. So as you can see, the NetVM follows the theoretical line. However, we have a little slowdown in the click on NetVM, but after the 128 packet size, it follows the theoretical line. And this shows the inter-VM forwarding. the performance, we use the mix of L2, L3, the forwarding, and the custom firewall. The custom firewall does only address filtering. And as you can see, after 3 VMs chained, that our performance degrade because we actually shorten the number of cores that we used for the virtual machines. However, if we deployed like a little bit realistic the scenarios, like a 60% chained through the virtual machine, but the 40% like go inside the virtual machine and coming up. Okay, so in that case, we actually perform like almost 10 gigabps for the 5 virtual machines. Okay, this shows how flexible our system is. The load balance based on the queue size of each virtual machine. So you actually the NetVM the performs like a perfect the load balancing in the system because we have a capability to see the queues of the virtual machines. However, the SRIOB is limited because it has the static configuration to forward the packet based on the L2 address. All right. This is the last one. Okay, conclusion. We propose an NetVM, the high-performance network framework in the virtualized commodity platforms. We have a series of the innovations like a virtual machine-based high-speed packet delivery, memory sharing framework for the network data, and hypervisor-based switching and high-speed inter-VM communications and the security domains to provide security between virtual machine. Okay, I will stop here and I will take the questions.
So we have time for a couple of questions.
Again, one from Cisco, and very nice talk. So I've been working on this area too. Working on user space drivers, and then doing like operate with the TXRS queues like from the application. I think it's a de facto standard to get the packets like fast getting into the application, and then like packet fast actually getting it out. So I know that the reality, but the reality is this is a question about the programming model. So people are so accustomed to use like socket interface actually to program the networking. And then if you move on to that area, it's completely different world. So do you have any perspective about I think the beauty of the previous work, actually you mentioned that the NetMap, actually the beauty of that is actually you can use like very socket kind of like interface actually to program it, right? So that's my first question. And second question is, before I forget it. So second question is, how many part of the code actually you have to touch to make this work? Did you ever touch that the Intel driver code like from the bottom? Did you ever touch that the hypervisor source code? And then do you have to touch that another actually Intel driver running on the VM? So that's my question.
Okay, thank you. That's good questions. Actually, the first question is how do we deal with these protocol stacks? So these are all the middle boxes targeted. So middle boxes like handle packets by packets, right? However, there are some softwares running in the application like MTCP, the following the presentation, and they provide the user space, the network protocols in it, and that's one. And there is like a KNI. That means that once you get the packet, you can actually push that packet into the kernel space, so you can still achieve the same thing, but there is some overhead. So that's a second. So the mostly people actually use the custom, the protocol stacks in their systems. So the Wind River, these systems actually they sell the user space protocol stack. The second thing is how much I touched for the implementation. So we modified some of the functions in the KVM side in order to achieve this the queue and the core alignment. And we for the only existing systems, the KVM is modified, and we added the PCI device to the KVM, and we actually didn't touch anything about kernel modules. So we didn't the kernel space. So we only had this user space I/O, the kernel module to achieve this. So the basic.
Quick question: do you have to dedicate the one interface to one VM to make this work, or can you still do that? One traffic from the one interface can go to 2 VMs.
So we can achieve there are multiple VMs. Yeah, but to see the performance, the maximum performance that we dedicated to the one VM to the one core to the one VM.
And then you still need to touch some code in the driver, like Intel driver.
We should probably take this offline.
Okay, sure.
Thank you. Let's thank the speaker again.